Hello and welcome to another edition of OntologyTalk. I'm Adam Pease, and today I would like to talk about the notion of demystifying automated reasoning. And this is just an introduction and an overview, and then we'll have some more detailed videos on the specifics of how to actually do this sort of thing. So first off, what is automated reasoning? There are many sorts of reasoning or inference, and especially today I read a lot of headlines or titles talking about doing inference, including things like textual inference. And this is a very general word, right? So it can be used a lot of different ways. And the way that I'm going to use it here is the usage in the automated theorem proving community that does work in reasoning and mathematical logic. And here I mean it's the use of computer software to approximate a certain kind of reasoning, deductive reasoning, using symbols, using a mathematical logic or some other kind of mathematically formalized system that's objective, repeatable, it's not stochastic, it's deterministic, has all those qualities of a mathematics. There are many kinds of different kinds of mathematical logic. One of the most basic is propositional logic. So you might remember this from schooling at some point, if you had a scientific and technical education. So here's just some examples. A propositional logic has no variables. We take statements in natural language, like Mary likes cake, and we assign it a symbol. In this case, P, or another statement like Mary likes cookies, and we can assign it a different different symbol, Q. And then we can make statements combining these symbols such that if Mary likes cake, then Mary likes cookies, or in propositional logic, P implies Q. And you can string together these sorts of statements according to these symbols in propositional logic and do some very simple kinds of inference. So if, for example, you have this rule P implies Q, and you know P, then logically, necessarily, according to the mathematics, you can derive Q. You know Q is true because P is true and P implies Q is true. So this is the most basic kind of logical symbol structure in logical mathematics. But this is very limited. Propositional logic is really used more often as an introduction for students these days into what's possible. It's not really a very terribly useful system of mathematical logical reasoning. So, for example, we can't say that Mary likes food X that has sugar. If she likes food X that has sugar, then she'll also like any other food Y that has sugar, because we don't have any variables. So we can't talk about these abstract things like X and Y. And hopefully this should be clear that even if you've done any just basic algebra, you need variables in order to do most useful things. So another kind of mathematical logic is predicate calculus, or otherwise known as first-order logic. And this is the kind that I'm going to talk about today and in subsequent videos, but I want to give you a little context. It is the most common kind of classical logic or two-valued logic, a logic in which has just true or false and not I don't know or unknown or in between or sort of or any other kind of constructs like that you might imagine that we can communicate in English. It's pretty strict, just true and false. It is a good compromise between speed and the expressivity of the statements. Expressivity refers to the notion of what can you say in the language and have it be expressed logically, strictly, with capturing the full semantics or meaning of that statement in this particular language. So propositional logic, as we've just seen, has very limited expressivity. It doesn't even have variables. So there's lots of things that you'd want to be able to say in English or in any other natural language that you just can't say in a propositional logic. So having a more expressive language, absent all other qualities or issues, is a good thing. But there are other qualities or issues. So the more expressive you are, the more difficult the mathematics is, and usually the more difficult, complicated, and predicate predicate calculus or first order logic is generally seen as a kind of a good compromise. We know how to do fairly efficient inference with it, and it has lots of very well tested implementations. It's fairly expressive, but certainly different people can make different choices depending upon the needs of their applications or their scientific interest. So there are lots of others. Other kinds of mathematical logic, description logics, are quite popular today. They're very efficient, and they were chosen, I think, primarily in the early 2000s as a better compromise between speeds and efficiency, because first-order automated reasoning wasn't as far along. It wasn't as advanced. It wasn't as fast. And at the time, people were quite concerned about having inference that could terminate in a reasonable amount of time. I think that concern is changing because the automated reasoners have gotten so much better. And there are, unfortunately, once you've made that choice to use this more constrained and computationally efficient logic, description logic, you have a lot of restrictions. It doesn't really have true variables. I've talked about this in another one of my videos. It doesn't really have proper quantification. It doesn't have true negation. It doesn't have functions. It only has binary relations, and so on. So quite a lot of severe restrictions on what you're allowed to say in the language. For some of these, there are workarounds. For others, there are not. I personally think it's too many restrictions to be able to encode the most important things that we know about our world. On the other side, there are modal logics. I won't go into much detail right now about what those are, but let's just say that they're more expressive than first-order logic. Includes all sorts of qualifications, such as something happened during a time period, or this may become true, or it will become true, or it must become true, it should be true. All of these sorts of modifiers that we have in natural language are often termed as modals when you have a logical expression involving them. There are lots of options. Lots of people are playing around with different sorts of modal logics. There isn't a tremendous amount of standardization there, and there aren't a tremendous number of implementations of the same modal logic. So at the moment, I think that's probably not the best compromise for automated reasoning, although there's certainly some great and important research being done in those areas. A higher order logic, surprisingly enough, it's actually farther along in some ways, and it's more expressive than particular modal logics. In terms of the language, there's the THF standard in the theorem proving community, the typed higher order form, which is a classical higher order logic. Classical, again, meaning there's true and there's false. In terms of evaluating statements. It's getting better fast. We've done some experiments using the sumo ontology and the Leo 2 theorem prover that have worked out really well. Satellax is also a really great prover. I haven't worked with others, but there are many others that are quite sophisticated. And I think this area is the growth area. It is going to be what's necessary. We don't want any limitations really on what we can say formally. And there's still plenty of things you can't say in a first-order logic. Discussed this briefly in some of my other videos, but basically things like John believes that entire statement. John believes that Mary likes Sue. You're already in a higher-order logic. You have an argument that's an entire formula. And that can be computationally challenging, does require this other logic. But I think it's going to be a good option in the future. The key issue at the moment in some work that I've done with Professor Christoph Benzmueller is that even for something like sumo that's expressed in a higher order logic that has lots of modal operators, like qualifying something of the time that it was true, and at the same time talking about a belief that somebody may have. So if you want to say, John believed in the year 2000 that vaccines were a bad thing, but now he's changed his mind. That's something that requires combining two modal logics. That's, I think, one of the hot research areas, something that needs to be resolved before we can use a theory as sophisticated as sumo in a higher order logic theorem prover and get consistent results. We know that this is a challenge going forward, but I think it is the way forward. But in this talk, just to be clear, I'm going to talk just about first order logic, because that's what we know well. There are good provers for it, etc. All right. So I'm going to divide this into a couple of parts. We're going to do this over several videos. First, I'm going to give you an algorithm and an example and an implementation. Also, I should talk about what's not covered here. So automated reasoning, even in first-order logic, is a tremendously rich area. There's a conference, an international conference, every single year, the Conference on Automated Deduction, and its corresponding international conference that convenes every 2 years, the International Joint Conference on Automated Reasoning, IJCAR. And so I couldn't possibly begin to cover what's in those conferences. If you're at that level of depth, you're probably already aware of this stuff. You may know more than I do about it. Here, I'm just going to try to explain in a way suitable for helping programmers and people new to this discipline what is the simplest base case. I'm trying to demystify it. How can we show what this sort of area is capable of? Because it often is presented in a highly mathematical and difficult to understand form. So I'm just going to show the simplest base case of automated reasoning using proof by refutation, which is sort of the standard algorithm. But I'm not going to show any of its embellishments or enhancements. In particular, I'm not going to talk about superposition. And this was a big advance that allowed first-order reasoning to be done efficiently with equality. And it's hard to do without equality, so this was a big roadblock up until the superposition algorithm and something called Knuth-Bendix ordering was discovered several decades ago and then subsequently implemented in the best provers. So there's really only two steps if you want to summarize the approach. So first we have to take first-order logic and simplify it a bit. And so we simplify the language into something that's called conjunctive normal form, and that's what I'm going to talk about in the next video, is this process of normalization. And once you've simplified the language through a simple, somewhat simple mechanical procedure, then you can actually run inference. So I'm going to talk about those each in their own video. So that was it for the introduction. Please be sure to watch the next video on normalization and its details. And if you like this, subscribe and comment. Thanks very much for watching.